Hey there, Keys Pre-Calculus. We're going to do section 3.4 in the book. We did most of it in class. I'm just going to work a few more examples here on the video. We are solving exponential and logarithmic equations. And if you remember, we said your first goal, if you can, is to write your equation, either exponential equation or logarithmic equation, with the same base, and then use the one-to-one property to finish solving your equation. If you can't get the same base, though, then you need to either might need to rewrite an exponential function into logarithmic form and apply the inverse property of logarithmic functions, or you need to take a logarithmic expression and rewrite it in exponential form. In other words, exponentiate it and use the inverse property of exponential functions. However, using that second one is the same thing as really using the definition of a logarithm. So any way you look at it, either way you look at it, you can still get the same result. We did several examples in class. I'm going to do a few more here on the video. They should all be in your book, but I'll talk you through them. Here's another example that we did not do in class. Solve for x. You can see x is in the exponent. So if we can't find the same base, which we're not going to be able to do because we can't make the other numbers have a base of e, then we're going to have to take the natural log of both sides. But before we do that, we need to get this expression that has the 2x and the e by itself. So what we're going to do is we're going to add 3 to both sides and divide by 4. And when you get that, you have e to the 2x equals 5 over 4, or 5/4. Okay? You can't turn 5/4 into the base of e and get the same, to get an equivalent expression, to use one-to-one property. So you're going to have to take the log of both sides. So we're going to turn this into a logarithmic equation by taking the natural log, because we want to take the log with the base of e. So that's the natural log, e to the 2x. And whatever we do to the left side, we have to do to the right. So we take the natural log of 5/4. We can, by the inverse property of logarithm, we know that when we take log base e of e to an exponent, it's equivalent to that exponent. So essentially, these cancel each other out, and we're left with 2x. 2 times x equals log of 5/4. Now, I want x by itself, so I need to divide both sides by 2. This is not dividing 5/4 by 2. This is dividing the natural log of 5/4 by 2. Okay? And when you do that, then you need to use your calculator, and you would type in natural log, parentheses, 5/4, close parentheses, divided by the whole thing. Or you could hit return and then divide the whole thing by 2, or you should be able to just divide the thing by 2 and get 0.112. Okay, so that's how to solve when you've got a variable and an exponent with a base, when you cannot find the same base. You're going to take the logarithm of both sides and then simplify it that way. Okay, I put a couple of other problems up here. I was skipping around in class, so I cannot remember what we did do and we didn't do. Let's look at this blue equation. This says take the natural log of x, or the natural log of x equals 2. Solve for x. So first we ask ourselves, is this something that has the same base? Can we use one-to-one? No, we cannot. This is a logarithmic equation. I can't just take the x out. I can't subtract, add, multiply, or divide anything. So I can't just divide by x or divide by ln or anything like that. So what I have to do is I have to exponentiate the function. At least that's what one way to approach it. So I could say I need to take give each one of these a base and raise and let the left side be an exponent and the right side be an exponent. And I'm going to give them the same base as this log. Natural log is base e. So I would say the same thing as e. Natural log to the x is equivalent to, I have to do the same thing to the other side, e to the 2. Now, e natural log of x, these cancel each other out by the one-to-one property, the logarithmic one-to-one property, and I've got x is equal to e squared. And then when I type that in my calculator, I get x is approximately equal to 7.389. Okay, that's one way to think of it. The other way to think of it is log of x, log base, or natural log of x is the same thing as saying log base e of x. I would be doing all of this in my head, not on paper, but I'm doing it on paper to show you. This, and by definition of logarithm, this would be saying this base raised to the second power is equal to x. So I would go straight from the original natural log of x equals 2 to this bottom line that I wrote, e squared equals x, because I would do it in my head, but I was showing you on the video. And then I would just use my calculator to simplify it to get 7.389. Okay, so now let's look at this red equation. I'm going to give you a second. I want you to see if you can see initially what to do. All right, if you look at it, you see that both of these sides have the same base. They have log base 3 of some value on both sides of the equation. That means by the one, I can use the one-to-one property. And by the one-to-one property, remember log base a of x equals log base a of y, if and only if x equals y. Well, if we set 5x minus 1 to x plus 7 and solve for x, we can make this a true equation. Or I should say, this would be true if 5x minus 1 equals x plus 7. So we're letting that be true, and we're going to solve for x. So I'm going to subtract x from both sides, and I get 4x equals 8. Divide both sides by 4, and I get x equals 2. It's within my rules, therefore x equals 2. Now, I'm going to come up here and check it. 2 times 5 is 10. 10 minus 1 is 9. And then 2 plus 7 is 9. And 9 is a positive number. That's not 1. So it works. Now let's take a look at this example. It is similar to the ones that we've been working on. However, there is something different about it. It's a little more complicated. We can still solve it, however. Study the equation. See if you can recognize anything here. I really can't combine the first two terms because they're not like terms. I don't need to move my 2 over. I've got this trinomial here that is in quadratic form. Although my variables are in the exponents and my e is a base, not an exponent, I can still factor this like a quadratic. What times itself will give me e to the 2x, or yeah, what times what will give me e to the 2x? Couldn't e to the x times e to the x give me e to the 2x? Right? So let's go ahead and use that to factor this as if it were quadratic. So if I wrote e to the x times e to the x here, but I've got to add or subtract something from here because I'm factoring it. What two numbers can I multiply to get a positive 2 but add to get a negative 3? Well, that would be negative 1 and negative 2. Because negative 1 times negative 2 gives me positive 2. And then negative 2 e to the x minus 1 e to the x gives me negative 3 e to the x. So do you see how we factored it just like a quadratic? And then I can set each one of these factors equal to 0. E to the x minus 1 equals 0. Or e to the x minus 2 equals 0. If I add 1 to both sides on this one, I get e to the x equals 1. Add 1 to both sides, I get e to the x equals 2. Now, I've got 2 equations to solve. I can't change 1 into a number with a base of e. I can't change 2 into a number with a base of e. So I need to take the logarithm of both sides. So I'm going to take the natural log of e to the x equals the natural log of 1. When I do that, these cancel each other out, and I've got x equals the natural log of 1. Now this goes back to one of our properties. Log base e of 1 equals x. Anytime I've got log base anything of 1, I know that that anything is going to end up being 0. Because I have to raise any number to a 0. I said that backwards, but I meant log base anything of 1 is going to have to equal 0. Because anything raised to 0 will give me 1. All right? So that's one of the equation, or one of the solutions. Now I need to solve the other one by taking the natural log of e to the x equals the natural log of 2. And again, these cancel each other out using the inverse property of logarithms. And I get x equals natural log of 2. And when I put that in on my calculator, x is approximately going to equal 0.693. Right, you'll see how that works, like a quadratic. Pause the video and study it for a second if you didn't see it right away. Okay, here are a couple more examples to go over. Solve for x. Okay, well, I need to get this term with x in it by itself. So I'm going to subtract 5 from both sides here on this blue equation, and I'm left with 2 natural log of x equals 5. Negative 5 plus 4 is negative 1. Now I'm going to divide both sides by 2 because I want to get this by itself as simple as possible. So equals negative 1/2. So log base e of x equals negative 1/2. Okay, I can solve this because I'm not taking the log of a negative number. It just happens to end up being a negative number. But I can't get this x by itself. I can't divide by the natural log. So I'm going to have to exponentiate it or use my definition of logarithms. Remember, log base b of x equals y if b to the y equals x. So I can just take this base, raise it to the negative 1/2, and that would equal x. I could also exponentiate it. I could say e, which is the base of natural log of x, and I could equals e to the negative 1/2, and remember these cancel each other out. So that's an alternate way to think of it, but I'm not going to, well, it doesn't matter. You can think of it any way you want. I always think of it the first way, but if you think of it the second way, that's great too. They're both correct and not really different from each other. It's just another way of thinking about it. Okay, so now when I finish solving for this one, I can just type this in on my calculator. And I'm going to get x is approximately equal to 607. I mean, I could finagle this around and say this is the same thing as saying, 1 over e to the 1/2 equals x, which is the same thing as 1 over the square root of e. But that's not simple, and I don't need to do all that business. I can just type it in on my calculator and get x is approximately 0.607. The red equation works almost the same way. I want to get this term with the x by itself as simply as I can get it. So I'm going to divide both sides by 2. And so I have log base 5 of 3x equals 2. And now I can use my definition of logarithms. 5 squared is equivalent to 3x. 5 squared is 25 equals 3x. Divide both sides by x. Or excuse me, divide both sides by 3. And I get x equals 25 thirds. Or that goes into there, what, 8 1/3? Is that the answer? Either way, it's fine. Or you can actually divide it out with your calculator and give a decimal if you want. But a fractional answer is fine too. I'm going to do one last example with you. This is example 9 in your book. I'm going to ask you to study examples 10, 11, and 12 on your own before you do the homework, because we're running out of time, and those are something that you can just, I'd like you to study on your own. But on 9, it shows a reason why we need to always check our answers to see, and which we have not been doing, but we're going to do it with this one, and you should always look at it. Check your answers to see that they would work out and that nothing would give you an extraneous solution. So on this example, we can use the properties that we were doing in section 3.3. We can combine our natural log, because I'm taking the log base e of x minus 2 and I'm adding it to log base e of 2x minus 3. This isn't this is not in quadratic form, so I can't factor it or anything like that. So I'm just going to go ahead and combine them. So this is the same thing as saying log base e, or natural log of x minus 2 times 2x minus 3 equals 2 log base e of x, or 2 natural log of x. which actually I could rewrite that. Let me erase that. That can be also rewritten as the natural log of x squared. And you'll see why I'm going to do that in a minute. So here, if I FOIL out this x minus 2 times 2x minus 3, then I'm going to get log or natural log of 2x squared minus 3x minus 4x, which gives me negative 7x. And then negative 2 times negative 3 gives me positive 6 plus 6 equals the natural log of x squared. Now, if you look at this, you can see that I've got two logarithms with the same basis on either side of my equation. Therefore, I can use my one-to-one function. I can just drop the natural log, and I can say 2x squared minus 7x plus 6 equals x squared. And now I can solve it normally. So I'm going to subtract x squared from both sides, and I'm going to get x squared minus 7x plus 6 equals 0. Okay. Can that be factored? Yes, it can. I can multiply two numbers to get a positive 6 and add them to get negative 7 when I use negative 1 and negative 6. So x is either going to be equivalent to 1 or x is going to be equivalent to 6. But I need to change, because I've introduced extra numbers in here, I need to check them to make sure that they work. So if I substitute 1 in for x up here, and I'm just going to do it in red so it looks a little different. So I'm going to put 1 minus 2. What do I get? I get a negative 1. Can I take the log of a negative number? No, I can't. Therefore, this one down here, x minus 1, is an extraneous solution because it gives me something that I cannot solve. But when I substitute 6 in here, 6 minus 2 is 4, so I can take the natural log of that. And 6 times 2 is 12, minus 3 is 9, and I can take the natural log of that, and 6 over here, it works. Therefore, I do not have to cancel it out because it's something that I can do. Therefore, x equals 6. And you should be really checking every single answer you get to make sure that it makes something, when you plug it back in, it makes something that can work. Okay, once again, study examples 10, 11, and 12 on page 211 and 212 in your book. Go back and look at these examples again and again until you have them until you're confident about them, and go ahead and do your homework. I will see y'all on Thursday. Have a great afternoon.